Welcome to this explainer. Look, if you're writing Python, you're already using data structures. But today, we're really looking under the hood to see how mastering Python's core organizers can fundamentally change how you model complex software. We're stepping way beyond the basic syntax to look closely at the underlying architecture. Here is our roadmap for today. We'll start with the concept of abstraction, dive into working with Python lists and their essential operations, introduce dictionaries, explore key value pairs, and wrap up by applying these models to real-world software.
All right, Section 1, Introduction to Abstraction.
Aho and Ullman really hit the nail on the head here. Computer science is fundamentally a science of abstraction. Before we even think about specific syntax or logic, loops, we've got to create the right model for our problem. When your datasets scale up into the millions of rows, it's these abstract models that literally keep the chaos at bay. We aren't just writing scripts, We're architecting data so our software can run elegantly and efficiently. Moving right along to Section 2, working with Python lists. So, what exactly is a list? At its core, it's an ordered, mutable sequence wrapped up in square brackets. And what makes Python lists so incredibly flexible, especially when you compare them to arrays in statically typed languages like C or Java, is that they handle mixed data types completely dynamically. You don't need to pre-allocate memory for one specific type of data. Integers, floats, strings, or even complex objects. They can all just hang out together in one single sequence. It is basically the ultimate dynamic grouping tool. Now, here's a quick refresher, and it's a big one. List indexing in Python is strictly zero-based. The first element sits at index 0, period. And because Python is just awesome like that, you can actually index backward effortlessly using negative numbers. Want the last item? Just call -1. Boom, you skip straight to the end of your data set without ever needing to calculate the total length of the sequence. It's a tiny architectural choice, but man, it saves countless hours of debugging off-by-one errors. You can really see this flexibility in action right here. Check this out. You can have a single list holding an integer, a decimal float, and a string right side by side without throwing any kind of type error. You can even deeply nest data, like throwing sublists of physics and chemistry grades inside a primary list. It basically lets you build a multi-dimensional matrix natively with just a few keystrokes. Okay, Section 3, Essential List Operations. Because let's face it, we don't just store data, right? We have to actually manipulate it efficiently on the fly. And Python's built-in methods are super optimized for this. Append lets you slap new elements onto the very end of a dataset, which is absolutely perfect for continuous data logging. Insert pushes data into an exact index, automatically shifting everything else down. You can delete by precise position or by the value itself, and instantly sort thousands of records up or down with just a single command. The heavy lifting of memory management is handled entirely under the hood. And all of those operations are possible because of one fundamental trait. Lists are mutable. Once a list is created in memory, it isn't locked down. You can grow it, shrink it, or just completely overwrite the elements in real time. This dynamic mutability is exactly why lists are your go-to structure for data sets that are constantly evolving, like processing a live feed of sensor data or managing an active queue of user requests. Let's pivot a bit. Section 4. Introduction to dictionaries. Sometimes numerical indexing just doesn't fit your data model. Think about the Contacts app on your phone. You don't find your friend by remembering they're the 42nd entry in your list, right? You look them up by their name. That's the key difference. While a list relies on sequential numerical ordering inside square brackets, a dictionary is mapped. It uses unique keys to instantly retrieve values, and everything is wrapped up neatly in curly braces. It's a massive, powerful shift from sequential searching to associative mapping. Which brings us to Section 5, Navigating Key Value Pairs. The anatomy here is actually pretty straightforward. A key points directly to a value, separated by a colon. But here's the golden rule of dictionaries. Every single key has to be completely unique and immutable, like a string, an integer, or a tuple. You absolutely cannot have two identical keys. If you assign a user ID as a key, it is locked in as a unique identifier. The values attached to those keys, though, those are totally flexible. That user ID key could easily point to a deeply nested, highly mutable list of preferences that changes every single day. And check this out. One of the absolute most efficient ways to interact with dictionaries is by using the membership operator, in. Imagine you're writing a back-end authentication system. You can use in to instantly verify if a username already exists in your database of keys. It evaluates to true, And boom, your logic executes immediately without iterating through the whole structure. It's a massively efficient O1 time complexity operation, which is literally a game changer when you're scaling up to millions of active users. All right, let's bring it all together. Section 6, Chapter Summary and Application. Let's actually apply this to a student record system. Instead of making the system search linearly through a massive nested list, we can model this using a dictionary. We assign the student's unique alphanumeric roll number as their immutable key and a mutable list of their latest grades as the value. Suddenly, searching for a specific student's record instantly becomes an O of 1 operation. From there, finding the top performer is just a matter of running standard built-in list operations like max or sort right on those mapped values. Or consider the architecture of a high-volume online banking app. How do you securely route thousands of concurrent transactions? You use unique account numbers as dictionary keys. This precise mapping lets the system instantly route deposits to the correct user, run quick real-time checks against minimum balances during withdrawals, and seamlessly calculate fixed deposit maturities across totally independent accounts. The data structure itself provides the speed and the security of exact routing. So as you can see, these abstract models, the highly flexible mutable sequences of lists and the precise associative mapping of dictionaries, they're the underlying engine of almost every piece of software you interact with today. They are what allow us to translate messy, chaotic, real-world information into structured, solvable code. Now that we've reviewed the architecture, the only question left for you is, how will you model your next complex problem? Thanks so much for watching this explainer, and we will catch you in the next one.